Hello everyone. In this video we are going to talk about the shortest path algorithms and Dijkstra's algorithm in particular. But before we get into the working of the algorithm, it's very important to understand what does shortest path algorithm mean and what are the possible applications of such an algorithm. So basically, any problem can be represented in the form of a graph if we identify what to represent as nodes and what to represent as edges. So nodes can be computers, they can be cities, they can be buildings, they can be human actors, and edges between them could mean anything in the context of the problem. For example, if we are representing cities as nodes, then the edges could be the roads between those cities, or the edges could be any other kind of service that is available between those cities. If the nodes represent computers, the edges could be the network connections between those computers. Or if we have the nodes as humans, so the edges could be the acquaintance or friendship between people. So this way, any problem can be represented in the form of a graph if we decide what to present as nodes and what to present as edges. So once we have presented our problem as a graph, then shortest path algorithms can be used for optimization. So the possible applications of shortest path algorithms could be the use of navigator on Google Maps to reach from a source destination to a target destination following the shortest path. If the nodes are computers with edges as network connections and the weight represent the cost that a computer takes in order to receive a message and pass it on, so the optimization problem could be to find a route that would take the message from the source computer to the target computer, taking least amount of time. It may also help us to decide how to get to a target destination in our life when we have multiple choices. So our current state is where we are at the moment, what are the different possibilities that we can do and where it's going to lead us and how much it's going to cost, and then we can link them up in order to a state that we want to be in. So in order to get to that state, there will be multiple paths. However, the shortest path algorithm is going to make sure that we get to that particular state that we are interested in, which is our goal state, with minimum cost. So these are basically the different applications of the shortest path algorithm. So now if we talk in particular about the Dijkstra's algorithm, that is one of the oldest algorithms being used for shortest path. It has different variants. However, the one that finds the shortest path from a single source to all the other nodes is the most commonly used one. So we are going to look into the detail of the Dijkstra's algorithm and how it works, but before we do so, let's have a look at the assumptions of this algorithm. Assumptions of the Dijkstra's algorithm. So the first one is that it assumes the problem to be a single source problem. So we may not have multiple starting points, and therefore we have to have a single starting point or source in order to find the shortest path. So that is an assumption that has to be true in all cases when we are using this algorithm. The second assumption is that the weights are non-negative. The Dijkstra's algorithm does not work for graphs that has negative weights. Now you may think that in all the possible applications that we discussed, weight cannot be negative. For example, the time taken by a computer to receive a message and pass it on cannot be in negative. It may be a very small value, but still it's going to be more than 0. The same way, the distance between two cities cannot be negative. So in most of the real world problems, the weights cannot be negative. However, there are possibilities that weights can be negative. For example, in a business scenario, if we perform a task, it may cost us some money, whereas if we perform some other task, it may help us make some money. So in that case, costing money may be represented as positive and the earning of money may be represented as negative weight, or the other way around. So in that case, we may have a possibility where some tasks are going to let us lose money while others may let us make some more money. So one of them may be represented with a negative sign and other as positive. And if that is the case, then the Dijkstra's algorithm cannot be used for finding the shortest path. And then, although it's not an assumption, but it can be used for both directed and undirected graphs. So basically, if the graph is undirected, so we are going to consider them as both-way communication. However, if the graph is directed, then we are only going to follow the flow of the arrows. Next, we are going to discuss the algorithm. So at the start, we are going to consider to have a list that has all the nodes. So the first step is to have a list of all nodes with their weights initialized to infinity, apart from source that is initialized to 0, because we are already at the source and the cost to get to the source is 0. So we need to do some initialization in which every node other than the source node is initialized with cost of infinity, because we currently do not know what is the cost to get to that node, and the cost to the source node is 0. And the second step has to be performed iteratively. Repeatedly, we are going to pick a node, that is, pick the node with minimum cost and traverse all its edges. That is, have a look at all its neighbors and see if the weights could be updated. And in order to update a weight, we need to apply a formula. Let's say we are currently at u, so the source is u, and there is an edge from u to v, and since we are at u, so the cost at u is 0, and the cost at v, as we assumed earlier, is going to be infinity. So in order to decide whether we are going to update the weight for v is if the cost that we have currently at u plus the cost of the edge u to v is less than the cost of the node v that we currently have, then update the cost of node v. So in that case, d of v is going to be updated with d of u plus the cost of u to v. So since this is infinity, the cost that we have at source is 0. So whatever the cost of this edge is going to be, it's going to update the weight of this of the vertex v. So the distance of u at current point is 0. This cost, whatever its value is obviously smaller than infinity. So we are going to update this cost of the vertex d. And then we'll keep on checking this. If we have another possibility where this value can be even smaller, we are going to keep on doing this. So each time we reach a node, we'll have to traverse all its edges and see if the weights of the adjacent nodes could be updated. If we find a route that is providing a smaller value than the cost or the weight that it has currently, then of course we are going to update it. And once we have traversed all the edges of a given node, then that node is being removed out of the queue. So remove the node for which you have visited all its neighbors. So we are going to remove the node u from the list, and repeat the process and look again now for another node with the smallest cost. So the process will keep on repeating until we have all the nodes removed from the list. It may also be thought of as a reverse of this, where we have an empty list and we'll continue to add nodes to it until we have all the nodes on the list, which would mean exactly the same. So let's just do this with the help of an example. So let's say we have a graph that is having nodes A, B, C, D, and these are the edges that we have, and we will also have some cost with these edges. So the cost to get from A to B is 3, the cost to get from B to C is 7, the cost to get from A to D is 2, and the cost to get from D to C is 1. A is our source node or starting point, represented with double circles. So now, as we said in the first step of the algorithm, that we are going to assign a cost of 0, to the source node, because we currently are at the source node, and it's not going to cost us anything to get to A. And the cost to get to any other node is infinity at the moment, because we do not know what it is. So we assume it to be a very high value. And as we said earlier, let's use a different color. The cost to get to A is 0. The cost to get to B, C, and D is infinity, because we currently do not know how much it's going to cost to get to all these destinations. So as we discussed earlier, we need to maintain a list and put all the nodes in that list. So we have the node A that has got cost of 0. We have got the node B that has got cost of infinity. We have got C with cost of infinity and D with cost of infinity. So you may think of it as a dictionary in Python or an associative array in other programming languages. The nodes are the keys and the cost is the value. So we'll have to look for a node with smallest cost. So of course we are going to start with the source node. Then we have to traverse all the edges that we can get to from the source node, and we can get to two nodes from A. They are B and D, and the cost to get from A to B is 3. So using this condition, since 3 is less than infinity, so we are going to replace infinity with 3. So currently what we have identified is that the distance, the minimum or the shortest distance to get from A to B is 3, and this is what we have recently discovered. The same way, we discovered that to get from A to D is not actually infinity, but we can do so with a cost of 2. So we have updated the weights of B and D, because we can directly go from A to B and A to D, or in other words, they are the adjacent nodes of the node A, and from A we cannot go to any other node directly, so we are done with A. So we are going to get it out of our list. So now we have the node B, and the cost to get to B is 3, which is the updated cost that we have. The cost to get to D is 2, and the cost to get to C is infinity. So this is our new updated list. Again, we'll have to look in this list for the smallest value, and we found that D is basically the one that has got the smallest cost value, or the shortest distance from the node A, from where we actually started this. So what nodes can we traverse from D? So from D we can go to B, or we haven't associated any cost with this edge. Let's say it has a cost of 8. So if it has a cost of 8, in order to get from A to B through D is going to cost us 10. That is 2 plus 8 is going to give us 10. So we are talking about A, then to D, and then to B, which is costing us 10, while we already have a value of 3. So 3 is greater than 10, and therefore we are not going to update this value. From D we can also go to C, and if we go from D to C, that would be the cost that we accumulated while we reached D, so that would be 2 plus 1 equal to 3. So the cost from A to D to C is actually 3. While the current value that we have over here is infinity, so we'll update it to 3. So now these are the updated weights, and we are not going to check the cost of getting from D to A because A is already out of the list, and we are not going to find all the edges that leads us to A. So now we are done with D, and we are going to throw this out of our list as well. So D is done, and now we have B with the cost of 3, and we have C with the cost of 3 again. So we have got a tie, and we may pick any of the two nodes. Let's say we pick B. In that case, from B, as we said earlier, we are not going to check with A, we are not going to check with D, so we are only going to check with C. So the cost to get from A to C through B is going to cost us 10, which is higher than the value 3, and therefore we are not going to update this score. So B is out of the list as well, and then we have got C. Of course, we cannot go anywhere from C, and C will also be out of the list. So these are the updated costs or weights that we can have in order to get from A to all these nodes. So if we redraw this, this is A, B, C, D, and these weights are 3, 7, 1, 8, and 2. And the minimum cost from A to all these nodes is 3, 3, and 2. So that's how we can find the shortest path from A to all these nodes using the Dijkstra's algorithm. There is another way of demonstrating this algorithm that is a lot cleaner. So let's have a look at that too. Because over here too many cuttings can make it look ugly and we may lose the count. So therefore, let's try a cleaner approach to do the same. So we'll redraw our graph as B, C, D, and the weights are 3, 7, 2, 8, and 1. So now, as we said, we'll have to start with 0 cost for the node A, which is the starting node, and all the others are going to have a cost of infinity. So we can represent it in the form of a grid like this, where we have A, B, C, D, that is the total number of nodes that we have, and the cost that we have to all these nodes is 0 to A and infinity to all the other nodes. Now, as we were doing earlier, we have to pick a node with the smallest value, which is A. So we will pick A and find the shortest path from A to all the nodes that are directly connected to A. So the cost from A to B is 3, which is less than infinity. So this is going to remain the same as 0, and we have to update this to 3 because 3 is smaller than infinity, again using the same condition as we saw earlier. We cannot go from A to C directly, so it's going to stay as infinity. And from A to D, we have a cost of 2, which is smaller than infinity, so we are going to update it to 2. Now we are done with A. So we have to pick a node from these ones in order to proceed further. So the smallest value among these nodes is D, which has a value of 2. So now we have to look for all the possible shortest paths from D to all other nodes with which it has got direct connections. So we are not going to change this one, so it's going to remain the same. This is also going to stay the same because we are at D and we are not going to check how we get there. And now from D we can go to B and we can go to C. To get to B, it's going to cost us 10. So we are not going to update this value and it's going to remain the same as 3. To get from D to C is going to have the cost of D plus the cost of this edge. So that is going to cost us 3, and we are going to update this value. So now we are done with D also, and we are left with B and C. As we have a tie, so we can pick any of the nodes. If we pick B, so from B again we have to keep A and D unchanged because we are already done with that. We are also going to keep B the same because we have already got to B. Now from B we can possibly go to C, and that is going to cost us 10, which is higher than 3, so it's going to remain the same. And finally, if we take, and finally from C we cannot go to any other node, so this is the cost of getting from A to all these nodes. The cost from A to A is 0, from A to B is 3, from A to C is 3, and from A to D is 2. That is the minimum cost. So that's how we can run the algorithm on any given graph and find the shortest path using the Dijkstra's algorithm to all the other nodes in the graph. Now let's run through this algorithm once again, and this time we'll do it for a directed graph. So for that we'll redraw the same graph, but this time we'll add some arrows in order to make it a directed one. So A, B, C, D. This is the graph that we used earlier as in an undirected form, and these were the weights. But this time we say the graph is directed. So let's say this edge is bidirectional. This edge is directing from B to C. Then this one is from C to D. And this one from A to D. So we have added some directionality to the graph in order to make it a directional graph. And again, if we follow the same mechanism, we can find the shortest path from A to any other node using the same algorithm, as it treats both directed and undirected graphs the same way. The only difference is that now we are only going to traverse the edges through their directions. So again, if we draw the same grid, we have the distance from A to A is 0, and from A to any other node is infinity. 0 is going to remain the same as we are starting with this node, and onwards from A we can go to B with a cost of 3. We can go from A to D with a cost of 2, and we cannot go from A to C directly. Next we have to pick the shortest value other than A, so that is D. We'll use D. Now from D, or let's say this one is pointing upwards. So A is done already, so we are not going to change its value. We have already got to D, so again its value is going to remain unchanged. From D we can go to B, and that is going to cost us 10. That is, currently at D we have a cost of 2, and further we need to add 8 to it. But we already have a cost of getting to B as 3, which is smaller than 10, so we will remain with 3. From D, we cannot go to C in this case because there is no edge that could take us from D to C, so this is going to remain as infinity. So that is basically the difference between directed and undirected graphs, that now we can only go through or traverse the edges with their directions. Now we are done with A and D, and we have to pick the small value between B and C, which is B. So we'll start with B. These two are going to remain the same. In fact, this one is also going to remain the same. From B we can go to C, and the cost is going to be the cost that we have at point B plus the cost of this edge, which is 7. So the value is going to be 10. So these are the shortest paths that we can get from A to any other nodes in this directed graph. Finally, we are going to talk about the time complexity of the Dijkstra's algorithm. Time complexity of the Dijkstra's algorithm can be observed in two different ways. The one that we are using so far in our algorithm is basically going to have a time complexity of N, that is the total number of nodes that we have, plus E, that is all the edges that we have, with log of N. Now let's have a look how we came up with this complexity. We are repeating the process for all the nodes. So that means the number of nodes we have to repeat this process for all the nodes. Then we are traversing all the edges of each node. So the number of edges that we have comes over here. And this log n part comes for the selection or the search algorithm of picking the node with the smallest value, because each time we have to pick a node, first we'll have to look for a node with the smallest value. So this is basically representing that search algorithm. So that's why our cost or time complexity is basically consisting of the number of nodes that we have plus the number of edges multiplied with log number of nodes. So it's a log linear time complexity. Its complexity can also be represented as n into n or n square in a case if we do not use any intelligence and find the distance of all nodes from all other nodes. So we have picked a node A without using any heuristics, and we have find the distance from A to all the other nodes. Then we picked another node and find the distance from this node to all the other nodes, and repeat the process for all the other nodes. And each time we find a case where a weight or a cost could be updated, we do so, otherwise we move on to the next node, and then we do so for D also. So we are finding a combination of all nodes to all other nodes, so that would have a time complexity of n square. However, as we observed that if we have checked all the edges from A and we have updated those values, so then there is no need to check for A again, because the costs are not going to be updated again. These are the best values that it can get and they are not going to change. The same way, if we are done with D, the values for D are not going to change, so checking them over and over again is not going to make any sense. So if you are using those kind of heuristics as we did in the algorithm, this is going to be the time complexity. However, if we just check the cost of all nodes to all other nodes, in that case the time complexity is going to be n square. So that was all about the shortest path algorithms in general and the Dijkstra's algorithm in particular. The Dijkstra algorithm has a problem that it cannot deal with graphs that has negative weights. As we saw in the assumptions also, that it assumes all weights to be positive. So if that is a scenario where we actually have a graph with both positive and negative weights, so if actually we have negative weights in the algorithm, how we are going to tackle with it, we'll see it in the next video. Thank you.